We're going to take a look at the vapor liquid ideal solution problem that was given in class. I had done this in class, but I when I had Zoom on, I didn't have this recording or this active screen sharing this screen, so I'm gonna repeat that a little bit. We have Raoult's law. We know that the uh, vapor pressure of A is 90 kilopascals and B is 50 kilopascals, and we know the overall composition and the fraction that is vapor. So this is a what is called a flash calculation. If it was dew point and bubble point, it would just be the first little bit of either vapor or liquid. In this case, it's in the middle. We have some kind of fraction, so we need to do a material balance in concert with the um, equilibrium, their Raoult's law for both A and B. So I've just put these in, these first few things in from the problem statement, and I'm going to do Control Shift F3 to go ahead and name those. So I've got all these named. The next step, you can do the algebra on this problem, and it's really not that bad. I'm demonstrating how to use solver, so this is the numerical methods portion of the class. So I want to so we're going to guess the values. So the P, I'm going to guess somewhere in between 50 and 90. We have mostly A, or I'm sorry, mostly B. So I'm going to guess closer to B, say 60 for my pressure as a guess. And it wants the mole percentage of A in the liquid. So I'll guess XA and then XB or YA. And we'll say XA is it's 0.1 overall. So this A is the more volatile component. So it's going to be less in the liquid. I'm going to go with 0.05 and 0.15 in the vapor as my guesses. And those will probably be fairly reasonable guesses. And I'll go ahead and Control Shift F3 to name those also. Okay, so now I'll just put the units in here. Now I'm going to put down Raoult's law. And instead of writing at 1, the liquid equal to the vapor, XA, PA vap, YAP, I'm going to go ahead and use them set equal to 0. But before I do that, I'm going to just do the kind of the equations that are just going to be simple, that are going to make the calculations a little bit easier. For instance, I'm going to put in XB here and YB, and I'm going to put in the liquid fraction in here also. I could put them in the equation as 1 minus XA, but this will just clean up the equations and make them a little bit smaller. When I do that, I'll go ahead and name these cells too. Control Shift F3. And we'll just say this is equal to 1 minus XA. Binary system, so these have to add to 1. Minus Y, and that looks about right, and equal 1 minus the vapor fraction here. And there we go. So these are the mole fractions equal to 1 in each phase, and then also the liquid and vapor fraction have to equal 1. And so now we're going to put in the, we'll do the material balance. So these are our calculations. Well, I guess these are calculations too. And we're going to do the mole fraction, or the overall material balance. I'll put that in as a comment. On A, we kind of did the overall material balance on the overall one when we said the vapor and liquid have to add to 1. We'll just assume that it's 1 on the, okay, so here we go. We're going to say that equals, again, that XA we'll take a basis of 1 mole total. Let me just do that. In tote. It'll just be 1, and that's our basis. Okay, and I'll go ahead and we can also say that ZA, I'll do one more, ZA B is equal to 1 minus ZA. Name those. Okay, now we're set to do our material balance. Let's do our material balance on A. So that's equals. Okay, we'll do the stuff going out minus the stuff going in. So, and we want this to be equal to 0. It will be when we have the right solution. So we're going to say equals ZA, or we're going to do the out stuff. Okay, so we got 2 streams going out. We got the liquid stream, which is XA times the liquid fraction, and this would be multiplied by 1, but I'm not going to get the number of moles, but since I took a 1, I'm going to not worry about that. And then I'm going to add in the vapor, which is YA times the vapor fraction minus the stuff coming in, or before, if you like to think about it that way, ZA times 1. Okay, that's not, well, I didn't guess correctly, so this is no surprise that that's not equal to 0, but we'll do now Raoult's law on A. So we've got equal to, I'll do the liquid first, XA times PA VAP minus the partial pressure, which is YA times the total pressure, which I've guessed at. And this should be equal to 0, but of course it's not because we don't have a good guess here. We're going to repeat that for we can do that for B also. Okay. And then what we'll do is we'll change these guesses here using the solver. We're going to set this is our objective equation. Okay. And we're going to make that equal to 0 by changing these 3. And then the Raoult's equations, we'll use those as constraints and make those equal to 0. And then we'll solve, and we should get the solution that you would get. And you can, of course, check the solution and make sure that it's good by looking at, well, you could do the balance on B and make sure that it's satisfied, and just make sure that everything adds to 1. You should get something, we'll probably get something a little different than this, of course, because we've got different values here, but it should be around this. So that was some, hopefully, help on setting this problem up, and kind of some of the things that I did in class that day that you might not have been able to see if you were on Zoom. So again, I hope that helps, and I will talk to you later.